Hi, it's me, Dr. Prasad Puthiyillam. Continuing my classes on ion exchange chromatography. This is class number 4. Some of the ion exchange reactions that I am explaining here. So, ion exchange reactions, if you consider, let us first consider the equilibrium reaction. Usually, in ion exchange resin, there will not be an equilibrium as such. Equilibrium will be shifted towards the right side. But if you consider the equilibrium reaction, say an example, Ra plus B plus gives Rb plus A plus. So here the ionic in the ionic form, the A is replaced with B plus, or A plus is replaced with B plus, or in this process we can say the ions A will go into the solution and replaced by B plus. Therefore, if you consider the equilibrium, so this is a double-headed arrow is indicated here. That means it is in equilibrium. Therefore, the equilibrium constant, or by the mass action law, the equilibrium constants, if you want to calculate, you can derive this expression that B bar upon A bar, gamma A bar upon gamma B bar gives K BA with B upon A and gamma B upon gamma A. So the letters which is given in here bracket, it denotes the concentration, and gamma, it is the activity coefficient, and the bar, this is B bar or gamma A bar, that bar represents that they are in along with the resin, or it is the resin phase. uh, this one rearrangement KBA, you can write it like this expression form. Here, if you consider this coefficient, that activity coefficient, that gamma term, if you consider it as a constant, then we can simplify this expression as KBA equal to concentration of A upon concentration of B into concentration of B bar upon concentration of A bar. So most of the reactions or the current reactions with a strongly acidic cases, that is H plus form, and it is used for the replacement of Na plus, or the purification of Na, or separation of Na plus. The reaction can be written as a RH plus plus Na plus gives RNA plus plus H plus. In this case, the corresponding selectivity coefficient can be written as KNaH equals H upon Na, and concentration of Na bar upon H plus. So here the coefficient what we written such a way that the H plus is replaced by Na plus. So that is the representation of the selectivity coefficient. For case of divalent ions, so in the previous case, if we see here the KNaH value, the coefficient value, it is found to be 1.7. That means in a standard gel type, it may be a sulfonic acid, strongly acidic exchange resin. Uh, the resin with the non-composition of Na plus and H plus ion is replaced in pure water. Sodium ion will migrate into the water until sodium concentration reaches the equilibrium. For a divalent ion, that is mainly we go for the softening reaction, that is calcium ions, magnesium ions, they are the divalent ions. Example, 2RNA plus Ca2 plus gives R2Ca plus 2Na plus. The selectivity quotient can be written as KCaNa gives Na upon Ca to the power 2, Ca bar to the power 2 upon Na bar. So, if we consider the regeneration of the ion exchange resin, the previous one we explained, if it is in equilibrium, what will happen. The regeneration cases, say example, regeneration consists of reversing the equilibrium in increasing the concentration of ion displaced in the equilibrium reaction. That is, whatever the ion that is replaced, we have to increase its concentration in the ion exchange resin column, then the reaction will be reversed. For an example, the softener is regenerated by using a high concentration of Na plus ions on the right side of the reaction. The reaction will be reversed. It causes the reaction to be shifted to the left side, and we'll be getting the regenerated ion exchange resin. Column operation, that is in the real practice, when we use the ion exchange resin for the application work, then there will not be in equilibrium. The reaction will either go in forward direction or will be in shifting in forward as well as backward direction. That possibility is also there. So in case of real operation, the resin is not left at equilibrium with the solution. The solution is withdrawn at the outlet of the column, so the equilibrium is always shifted, permanently shifted to the right side. Okay, so this is represented here, the same reaction that I used in the beginning. It will be shifted towards the right side. There is no equilibrium present here. So let us take the examples of some of the specific resins. The first one, that is strongly acidic resin. Strongly acidic resin, will be initially in the H plus form, that is RSO3 minus H plus. This form, H plus form of a strongly acidic resin, can remove all cations. So this is a cation exchange resin. It can remove all cations, that is represented here, RSO3 minus H plus. That is the along with the resin, H plus form. When sodium chloride is passed through that, it can replace, H plus will be removed with OH, Na plus will stick on to that resin. And this is even a reversible reaction. That means if you increase the concentration, if you pass HCl to the used resin, the reaction can be reversed, or we will get the regenerated resin. In case of calcium carbonate, calcium bicarbonate, or removal of the say example hardness, here it is calcium bicarbonate. The reaction is actually neutralization. This is a neutralization reaction, and it is not reversible. So you'll be getting H2CO, the carbonic acid is obtained by using the bicarbonate. If it is in initially in Na plus form, so when the resin initially in the sodium form, the strongly acidic cation exchange resin can remove even divalent cations from water, but not other monovalent cations, because the selectivity difference of the Na plus form in strongly acidic cation exchange resin with K plus or Na4 plus is almost the same. That means they cannot replace their value. The potential values are almost same. Therefore, the removal is not so easy. So it is not possible. Whereas with the divalent ions, cations with a two valency, Ca2 plus or Mg2 plus, that is possible even with the Na plus form. Okay, so RSO3 minus Na plus form. Initially, previous slide I explained about the H plus form. Here it is Na plus form. It can react, and possible reaction, which is also a reversible reaction. The next one, that is weakly acidic resins. In case of weakly acidic resins, we use RCOOH as the functional group in case of a strong weakly acidic resin. The weakly acidic resins, that means they are weakly ionized, and therefore with a neutral salt like Na plus and Cl minus, there is no reaction is observed, or there is no reaction as such, because if they react also, it will be for producing H plus Cl minus, that is HCl, that is a strong acid. The strong acid will convert the weak acid resin back to the acidic form. Therefore, even the salt formed, it will be converted into acidic form. Therefore, this reaction cannot happen. Whereas this weak acid resin, it can, if it want to react or if you want to use it, it must be dissociated. That is RCOH plus Na plus OH minus gives RCOO minus Na plus H plus OM, H plus OH minus, that is water, H2O. Then the following reaction, say RCOH plus Ca2 plus, that is a divalent cation. Reaction is possible, and it is even a reversible reaction. But this weakly acidic cation exchange resin, so it is not mainly used for the hardness removal, because of the possibility of precipitating calcium carbonate. With the sodium bicarbonate instead of calcium or magnesium bicarbonate, the reaction also occurs, but this weakly acidic resin has much less affinity for monovalent ion, so that operation capacity is low. RCOH plus Na plus plus HCO3 minus, reversible reaction, RCO minus Na plus plus H plus HCO3. Once converted this Na plus form, so this is the form RCOH is converted into Na plus form. This can further used for the exchange of divalent ions, that is RCOO minus Na plus Ca plus Cl minus 2 times gives RCOO twice Ca2 plus 2 Na plus Cl minus. The what I said that with the weak acidic resin, the softening is somewhat it is efficient for the separation of the hardness causing ions. Uh, the residual hardness in the treated water, if it is low, then this process can be done easily. And the next one, that is strongly basic resins. In strongly basic resins, the reaction the strongly basic resin, that will be the quaternary ammonium form. The functional group is quaternary ammonium form. If I abbreviate this the structure, if I represent simply as ROH, it can remove all anions from the solution, that is ROH plus Na plus Cl minus gives RCl plus Na plus OH minus. It can also exchange weak acids such as carbonic acid, that is ROH plus H2CO3 gives RHCO3 plus H plus OH. The reaction will not stop there, it will continue. RHCO3 plus HCO3 minus gives R2CO3 plus H plus OH minus, that is water molecule. Uh, the carbonate ion here, actually it sits in two functional groups of the resin. Uh, Even the strongly basic resin can react with a very weak acid such as a silica, that is SiO2, or boric acid H3BO4. For example, if silica is represented as H2SiO3, the reaction can be written as ROH plus HSiO3 minus gives RHSiO3 plus H2O. When strong basic anion resin is initially in the chloride form, that is Cl minus, it can exchange any anions for which it has a higher selectivity, that is RCl minus plus NO3 minus gives RNO3 plus Cl minus. So here this reaction represents the nitrate removal process, for which the special strongly basic anion exchange resin with different functional groups are used with increased nitrate selectivity. Now, weakly basic resin, the most common functional group is RCH2N CH3 dimethylamine functional group, and these are not ionized form in the regenerated free base form. Therefore, they do not react with the neutral salts like Na plus and Cl minus. For a weakly basic anion exchange resin to react, they must first be ionized. Only a strong acid can protonize the amine, which is transformed into a quaternary ammonium form, that is RCH2N CH3 twice plus H plus Cl minus gives RCH2N plus H CH3 twice and Cl minus. So the uptake of the reaction with H plus and Cl minus, it converts the weakly base anion exchange resin into the hydrochloric acid form, that is H plus and Cl minus. So here it's represented as H plus, okay, that is the positive charges on H, and Cl minus form. Therefore, this weakly basic anion exchange resin can mainly be used for the reaction with a strong acid only. So I think that's about the some of the reactions related to the ion exchange resins. Hope you understood this concept. Have a nice day.